Okay, hello everyone. Welcome to today's installment of Paleo Perks. We hope you're having a nice morning or afternoon or evening, depending on where you are. We're really excited about today's talk. We'll be hearing from Sonja Wahl, based at the University of Bergen in Norway, about the isotopic fingerprint of snow processes and their effect on the climate signal stored in ice core water isotope records. So a bit about the format of today's seminar before we get started. Right now, we'll start out with some welcome and announcements. After that, we'll have the talk, which should last about 30 minutes. And after the talk, we'll have a moderated question and answer session, which should last about 10 minutes. As a reminder, don't forget to send your questions to the questions at Paleo Perks host via the chat function. And today, the questions at Paleo Perks host is Aharna. A little bit of housekeeping. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself for the duration of your talk. You can ask questions by chatting to the questions at Paleo Perks host or by using the raise hand function. Technical issues should also go to the questions at Paleo Perks host. We have closed captions built into Zoom. You can use the CC button to show or hide them. Additionally, we are always on the lookout for outstanding early career researchers, and we'd ask you to nominate them at this link here, which will be shared in the chat shortly. Additionally, we do collect weekly feedback for demographic information. It's completely anonymous and completely optional, but it is encouraged and it helps us guide these seminars. You can also find that link in the chat window soon. So a bit more about today's speaker, Sonja Wahl. Sonja did her bachelor's in environmental sciences at the University of Tübingen in Germany, and then a master's in environmental sciences at the University of Hohenheim, also in Germany, and the University of Copenhagen in Denmark. She then went on to do her PhD at the University of Bergen in Norway, and is currently a postdoc on the Snow Dogs project at the Science Laboratory of Climate and the Environment in France, and at the University of Bergen in Norway. So with that, I'll hand it off to you, Sonja, and yeah, good luck and take it away.
Thank you so much. Okay, I hope you can hear me. I'll now share my screen and hope that this will work. Yes, so I think we are good to go. Thank you so much that I get the chance today to present my work. Thank you to Paleo Perks and the organizers of this meeting. So today we will be the motivation for my work for doing my PhD, but also now in my second postdoc during the Snow Dogs project, has always been paleoclimate and ice cores. But we will be diving into current processes, or generally processes that are happening in the snow. And we will be asking the question whether these processes are affecting the ice core signal, so the climate signal that we find in the ice cores. And yes, although I'm presenting, this is of course part of this is collaborative work that I've been doing during my PhD and the postdoc, and I'm currently actually, yes, both at the University of Bergen, but visiting the LSCE in Paris in France right now. This is the great information that we can get from ice cores. This is an example profile from the stable water isotope profile from a Greenlandic ice core drilling site, the NGRIP site. And you can see on the x-axis the time we can go back with this ice core, which is 120,000 years. And on the y-axis, you see the delta 18O, which is the stable water isotope record of this ice core. And you see that this signal varies quite a bit over time. So here is actually the current Holocene warm period, and there is the last warm period. And in between, you see the glacial and all the climate variability that happened during the glacial. And now I color-coded this delta 18O signal for you because we can actually interpret this as a climate signal. So where the lower values here are colder climates and the higher values are warmer climates. Now, this is Greenland, where we can go back 120,000 years. But then when we compare this to ice cores that we can find in Antarctica, we actually see that this is, in Antarctica, we can go much further back in time. So this is the EDC ice core, and you can actually see that there are 8 glacial interglacial cycles. So all the interglacials here, and this is the glacials, are recorded in this ice core. And now, just as a little peek, there's currently the challenge for oldest ice coring going on. So there's different nations all in Antarctica trying to find even older ice than 800,000 years. And I can just give a little shout out to the Beyond Epica Oldest Ice Core project that have recently actually had the success of covering or discovering even older ice than 800,000 years. So they are now reaching back about 1 million or even a little bit older. So hopefully spanning the mid-Pleistocene transition. But this is all ongoing project. So I advise you to just check their websites for updates. Great. So now, of course, though, the big question is, how do we get from this signal, that is the delta 18O signal, to a climate signal? Because this is what we're actually interested in, right? So we would like to know how warm or how cold was it back in time and what caused these climate shifts. And ice cores store a lot of this climate variability information at a pretty high resolution. But of course, we need to interpret this correctly in order to make the most of it, this information. And to understand or to really get the best or interpret this climate signal, the ice core signal, the best way, it's very good to have a thorough understanding of how this signal, how the climate signal is actually influencing the ice core signal. And I call this the transfer function. So basically, we would like to understand this so we can go back from the ice core delta 18O signal to our climate signal. Now, let's go back to basics. I just want to make sure that everybody is on the same page. Why can we actually use stable water isotopes as a climate proxy? Well, first and foremost, stable water isotopes are natural tracers in the water cycle, and it all comes down to fractionation during phase change. So let's imagine here we have this liquid of water molecules, and you see the normal H216O water molecules, but then sometimes there are water molecules that have a higher molecular mass and therefore are heavier. And this then leads to different behavior during phase change processes. So let's say there is evaporation happening, phase change processes happens, and now there's relatively less heavy water molecules being evaporated compared to the light ones. And this is what we call fractionation, and this process is temperature dependent. So this is where we have the first link to temperature. Now, just as a definition, we now describe this always as a ratio. So the ratio of heavy to light water molecules. And this is what we then translate into this delta signal. And here we would now, just as a way to describe it, say that the vapor phase is depleted compared to the liquid phase, and the vice versa, the liquid phase is enriched compared to the vapor phase in heavy water molecules. Great. And now, as another additional thing in stable water isotope research, we also would like to look at the DXS. This is a second order parameter where you just basically compute this DXS parameter from both the delta 18O signal and the delta deuterium signal. Great. So now another link to temperature we can draw when we then look at how the water cycle actually behaves globally, or the isotopes behave in the water cycle. So as a very first order principle or way to interpret the water cycle is a distillation process. So during evaporation in the equator areas, you have stable water isotopes that are being evaporated. And then during the progressive transport toward the polar areas, you have rain out. And this will then lead to progressively depletion of heavy water molecules. Now you can easily imagine that you need a bit of energy to get isotopes being evaporated. And then depending on how warm it is or how fast things rain out, it depends how many of these heavy water molecules arrive at the ice sheets. And this is exactly our link that we can draw from colder climatic conditions, less heavy water molecules that make it to the ice sheet versus then warmer conditions and higher stable water isotope values. Okay, and this is nothing new. People have been knowing about this for quite a while. So this is one of the earliest, I think, paleothermometer foundational papers where we have the mean annual temperature versus the delta 18O signal in the precipitation. Here you have European and I think American sampling sites, and then here we go to Greenland, and this is Antarctica, and you see this super nice linear relationship. And that's why we have been thinking, well, why, if we can do this now, why not look for old precipitation, conserved precipitation? And that's where do you look for these precipitations from past years? Well, you go to the ice sheets where layer after layer after layer, annual precipitation is piled up. It compresses, snow compresses into ice, and then these layers are conserved, but they flow out to the sides because ice is flowing and is not stagnant. And then the layers thin, but the information is preserved. So the deeper you go down in an ice core, in an ice sheet, the older your ice core will be, or the ice will be. And then if you have this ice core, you have a nice stratigraphy, hopefully, of layers of climate signal. Great. Now, the best thing about stable water isotopes, I think, is that this really works on many different timescales. So we can go back hundreds of thousands of years, but we can also be on the top of the Greenland ice sheets. And if I start digging down now for a meter, I also find summer values with higher delta 18O values and winter layers with lower, and I say automatically colder, delta 18O values. Okay, so this is the principle of the paleothermometer in ice cores. Now, this sounds all great, but as often in science, once you look closer, it gets a bit more complicated. Because of course now you would say like, wait a second, but are we then not biased to temperatures or the climate during precipitation events? Because if we are basically recording the climate of the precipitation event, then what if there is no precipitation happening? Then we're not recording the climate. So that's one big drawback that you can maybe say is a problem for for ice cores in general, but it's particularly for stable water isotopes. And the other thing is that it also assumes that this stable water isotope signal being brought in with a snowfall event is conserved and nothing happens to this stable water isotope signal in the snow. And that's really interesting that people have been thinking that for a long time, because although it might look very peaceful and as if nothing is going on here on top of the Greenland ice sheet, when you look closer, there's a lot of snow processes happening at the same time, continuously actually. So once we have snow recrystallization, so snow particles that are reforming, reshaping due to what we call snow metamorphism. This is a CT scan where under a temperature gradient, these crystals were recrystallizing into bigger crystals. Now, then there's also surface fluxes, so surface humidity fluxes that are being, here you can see them with an infrared camera on a white canvas. So there's energy and mass exchange at the snow surface. And also it doesn't always look as peaceful as this, but sometimes there is a little bit of wind which blows around the snow. And sometimes there's a lot of wind, which creates huge blowing snow clouds. And now the question is, do these processes affect the stable water isotope signal in the snow or not? And that's basically what I set out to do during my PhD, and also now I'm still currently investigating. Do snow processes like blowing snow, snow air exchange, so sublimation and deposition fluxes, or snow crystallization actually affect the snow isotopic composition, and are they important for the transfer function between the climate and the ice core? So maybe even are they part of it? And is this the reason, maybe are these processes one of the reasons why we can use the stable water isotope record as a climate signal? All right, let's start with this process, which is the sublimation and deposition flux. So as a very first experiment we wanted to do is like, let's just test it, right? Let's just put some snow samples of a known isotopic composition into a lab, into a cold laboratory box here. We put it in this box, 6 homogeneous snow samples. We had a lot of dry air circulating through this box, so a lot of sublimation was happening. And then we looked, and we took out, each day we took out 1 sample, sliced it up, and then looked for the isotopic composition and see if this was reacting to the sublimation or not. And this is what we found. So you have here the depth of the snow sample, and initially it was a homogeneous isotopic composition on the x-axis. But then with every day, you actually see that the isotopes change quite a bit. So the top surface gets enriched. And you also notice that these, of course, at some point we didn't have snow in the top layer anymore because it got sublimated away. So the surface also reduces. But after 5 days, there was actually an enrichment of 8 per mil, which doesn't sound like much, but it's in an ice core term, this could be glacial interglacial transition. So it's a lot of signal there. Great. And then for the delta, for the DXS, we saw an even stronger imprint of this sublimation signal. So initially this homogeneous here profile, and then a decrease of DXS over time. And after 5 days, we had decreased the DXS by 20 per mil, which is quite substantial. So take home 1, sublimation actually affects the snow isotope signal, and not only the very top surface, but several centimeters down. So you see even the lowermost layers were affected by this sublimation. Great. This was experimentally done in the lab. And then we went out into the field and to see whether we could measure these sublimation influence also in the field. So for this, instead of testing the snow, we actually thought, why not just measure the sublimation flux isotopic composition directly? So we set up this eddy covariance system and combined the eddy covariance system, which is something that measures the humidity flux directly above the snow surface, with vapor measurements of stable water isotopes that were drawn in here, this tube. The method is all a little bit complicated, but the results are really quite easy, I think, to understand. So here you have the delta 18O signal of the snow of all the observations that I made in one summer campaign of, I want to say 8 weeks, I think. And this is the delta 18O of the sublimation flux. And you see first that there's a relationship, a linear relationship. So I grouped these observations. And of course, this linear relationship is kind of what we expect because the sublimation flux comes from the snow. So you would think that there is a relation, hopefully, between the snow isotopes and the flux isotopes. But we can also see, and this is much more exciting, is that these observations, they are all below the 1-to-1 line. So this means that our snow isotopic composition is not the same as the flux isotopic composition, but the flux is reduced in stable water isotopes. So this means there was fractionation happening during sublimation. And that's really the fundamental basis for all of these snow processes having an effect or having potentially an effect for the climate signal, is that this sublimation signal can actually influence the isotopes. And this is what we have measured here directly in the field. Good. So this was focusing on snow air exchange during surface fluxes. And then I moved on to the bit more complicated process of blowing and drifting snow. But essentially, it comes down to the same thing. It comes down to, again, sublimation during blowing and drifting snow, because you can imagine that once the snow is in the unsaturated atmosphere, there's a lot of sublimation happening. And therefore, I was expecting to see a sublimation signal. But since it's a little bit tricky again to do this in the field, to observe these processes in the field, I went back into the lab, into the cold lab, this time in Switzerland, where we had at the Snow and Avalanche Research Center, SLF, we had this ring wind tunnel. It was sitting in a cold lab. And I was now making snow. So at SLF, you can make your own snow, which is really handy if you have to do these experiments in May, or maybe it was even July. So you can make your own snow. And then I also I know what the isotopic composition of the snow was in the beginning. And then the idea was I just throw it into this the wind tunnel, have it circulate in this ring wind tunnel, and take out periodically some of this snow to sample it and analyze it for its isotopic composition. And it looked like this. So this is the wind tunnel. There is, I hope you see this without a problem in my internet connection. So you see this snow is really transported in the air. And I have only sampled snow from outside this air column. So I haven't sampled any snow that was deposited to really see what is happening to the snow that is in the air. And now let's just look into what is happening inside the wind tunnel. So you see here on the x-axis, this is one experiment which lasted about 90 minutes. And here are the different variables that I measured inside the wind tunnel. So this is all the stable water isotopes, but let's concentrate first on the climatic variables. So here, for every experiment, I started the wind turbine. So we had some wind, and once we hit a certain wind speed, I started to throw in the snow. So that is the purple colored shading here. And then you see immediately once I have thrown in the snow, the relative humidity shoots up and is at saturation, which is what we expect when there's a lot of sublimation happening, right? The air takes up all the humidity it can get. And then the humidity, that is what you also see in the specific humidity, it goes up. And then we had this unfortunate thing for this experiment, actually, that inside the wind tunnel, the temperature would increase over time because the turbine was creating so much heat, actually. So this is why we see this continued increase of humidity, because the relative humidity is always at saturation. So you always have, if the temperature goes up, you have more humidity as well. But importantly, we see a change in the snow isotopes. So here, this is the vapor. The lines are the vapor isotopes, but this is the snow isotopes at delta 18O, deuterium, and DXS. And you see initially, I took 3 samples to make sure that I had a good handle on the first isotopic composition. And then you see that these samples that I took out of this wind or of the airstream do change in its isotopic composition compared to the initial. So here the delta 18O increased, the deuterium decreased, and the DXS decreased as well. And now I did this not only once, but I did it several times. And we're going to look at the maximum observed change in the snow isotopes. So what is the biggest change that I have observed per experiment? And here's this summary of the 19 experiments that I've done at different temperatures. The color code just means how much specific humidity change I observed, so how much sublimation was actually going on. And you see that you have quite a bit of change for most of the experiments. Sometimes for the deuterium, we had increasing and sometimes actually decreasing isotopic changes. And for the DXS, almost all the experiments showed a decrease in DXS, which is pretty similar to what I was expecting and also had seen in the other laboratory experiments with surface sublimation, right? All right, so now we have basically, yes, the take home here, the conclusion would be that, yes, blowing snow events, they also affect the snow's isotopic composition. And the question then is, of course, now if all of these snow processes that are happening continuously do have an effect, how much does it actually matter for the ice core and the paleoclimate signal, right? Because that's what we are actually interested in. And in order to answer this question, although I really love observations and experiments, I basically needed to transition into modeling this, because to quantify it, I think there is no better way in that moment here than to simulate your snow and ice cores and then to quantify an effect with or without these processes. Great. And so I started out very small with just looking at how much does my snow surface actually vary over time during one summer season. So this is the 2019 summer season. Again, we are in Greenland. And every day we went out and we took snow surface samples. So here this is snow. This is the purple dots that you see. And you see that they vary quite a bit over this 10 weeks period. And importantly, the gray shading shows you when there was snowfall recorded. But you also see that the snow surface actually changed in between precipitation events. So all of this here could not have been explained with precipitation events, but another process was responsible. And now, of course, we were interested to find out which is the process that influences the snow surface isotopes on these short timescales. And what you can also see here is the vapor isotope measurements that we took just above the snow surface. And you see that these both vary in parallel pretty remarkably. And this already, I think, hints to that there's a connection between the vapor and the snow isotopic composition. All right, so I set out to try to see if I could model my day-to-day variability. So this is what I'm going to call delta, a day-to-day variability of the snow isotopes, and we only look at the periods where there was no precipitation events. Okay, and the model we set up for this was basically assuming a snow surface isotopic composition, either through precipitation or because we observed it. Then we have sublimation happening in exchange with the vapor and the snow. And we have fractionation here. And then there is diffusion, because this is what we know happens in the snow continuously as well. And now the study basically tested two simulations, one where we had no sublimation effect and one where we turned on the fractionation during sublimation. And we tested whether this could give a better result. All right, and first I will show you the results of the experiment where we had no sublimation effect. So on the y-axis, you see our observed day-to-day variability. In a second, it's not there yet. And on the x-axis, you see how the model performed. All right. So this is the one-to-one line here. And this is what the observations showed us. So there were quite a few days where we had some pretty strong day-to-day change observed. But the model really doesn't do a very good job. It doesn't really simulate much change. And you see actually when you look at the color code here that net LE means that we have sublimation happening here on these days, net sublimation. So during days where there was a net sublimation, we also saw the strongest changes in the snow surface. All right, and if I now turn on sublimation and fractionation during sublimation, my model is captures this variability much better. So my R² increases quite a bit, which is the variability explained. And yes, so this made me pretty happy. And I think this is what led us to the conclusion that yes, sublimation actually helps in explaining the day-to-day variability that we see in the snow surface. And when you compare this to the, this is the deuterium. So for the deuterium, the variability was even better explained with the taking into account snow surfaces, sublimation during fractionation. Okay, and then day-to-days, who cares about day-to-days, right? We really want to go back to older, longer time scales and to something that is actually, you know, recorded maybe in the ice core. And so for this, we then performed simulations for a 30-year firn core at Greenland. And again, here you see two simulations, one with sublimation effects, which is the lighter colored, and one without the sublimation effects. And you see that we can make two observations really easily. Yes, the annual delta 18O signal gets increased, similar to what we have seen in all the experiments. It goes in the right direction. it increases the delta 18O signal, and the DXS signal goes down. So it's decreased when we turn on sublimation effects. Okay, but now what does a 6.3 per mil change in DXS actually mean? It's a little tricky to grasp what this means in terms of interpretation. Well, let's just assume that we interpreted this DXS as a source region signal, which is often done. So you can take the DXS and then interpret as the climatic conditions in the evaporation site. And now this is just a nice figure from an old paper just to help us explain this in an easy way. So let's assume we reduce the DXS by 6.3 per mil and then see what this means in terms of temperature change. And this is 15 degrees change in surface regions, source region surface temperature. Now this 15 degrees Celsius change could either mean we have changed the source region signal, so we have circulation patterns changing, atmospheric circulation patterns changing, maybe because of sea ice extent, or the source region evaporation area actually warmed or cooled by such a change in temperature. And that is, of course, quite a significant change then. Yes. Now, we still haven't really answered the question, does it influence the paleothermometer calibration, the way that we have been interpreting ice cores so far? And when we look at this just from a pure mass balance consideration, so are the regions on the ice sheets actually all influenced by sublimation, and how much does it matter compared to precipitation? You see here sublimation in percentage of monthly precipitation. So how much is sublimated after it is being brought in by snowfall. And this is the seasonal cycle. And you see that in the summer months for the Greenland, there is really months where there's up to like 20 to up to half of the mass that is brought in is actually sublimated away. So there's quite a potential for this process to have an effect. And when you then also think about it in terms of that there's not always precipitation, but sometimes there's periods in between precipitation events where the surface exchange is happening continuously, then you also see that this is spatially quite variable. So here there's very high frequency of precipitation events, but in the eastern Greenland, there's long stretches where there's surface sublimation happening, but no precipitation signal. So if then the climate signal gets imprinted by the vapor exchange, this would actually have the potential to influence our paleothermometer calibration function. All right, and basically, this is my last slide also almost, is that we have then tried to quantify this a little bit for the different ice core sites that we know of. And we have simulated 10 years of an ice core. And you see that here are how much each individual year is influenced by this surface exchange process. And you see that there's a lot of variability. So there's this is the mean, the black bar is the mean, and then this is the median. And you see that between the different ice core sites, it really depends how important this is for the DXS signal. And importantly, these changes in between ice core sites in the DXS can also be interpreted as different source region signals. But with the studies that I've shown you today, you could also interpret these changes in DXS here as a post-depositional influence instead of a source region signal, or maybe additional to a source region signal, because of course the source region signal is there as well. Okay, now this is just the surface sublimation flux. But we have talked about all the other different processes happening at the same time. And now, of course, the question is, what is the combined effect of all of these processes? And that's when you need not just the simple model that we have used so far, but you need a much more complex model that can actually simulate all these small processes. And this is what I'm going to do with the snowpack snow model that is usually used in alpine regions for avalanche forecasting and stuff like this. And I'm going to put stable water isotopes into this snowpack model, make it an iso snowpack model. And with this model, then hopefully actually simulating snow and fern and maybe even ice cores, who knows, to then really quantify how important these surface processes or post-depositional processes are for the ice core. Yes. Okay, so let's wrap this up. What I would like you to take home from my talk today is that I have shown that sublimation of snow actually influences the snow isotope signal on daily, seasonal, and annual time scales. That blowing snow events also change the snow isotopic composition during the airborne transport, and that the water isotope records are certainly influenced by post-depositional processes, and that these processes can imprint a climate signal that is in the vapor into the snow, but that these importance of the post-depositional process is spatially and probably also temporarily variable, and it's most likely most important at the low accumulation sites where the old ice cores are drilled. Yes, that's it. Thank you so much for listening. I'm very happy to take questions.
Great. Thank you so much, Sonja. That was a super interesting talk. We already have a few questions that have come in during the talk, but just a reminder to people in the audience, if you have any questions you'd like to ask, please send those directly to the questions at PaleoPerks host, and then I will post them in the chat and read them as well. But to get us started with our first question, we can just hop right into it here. Oops. This question reads, does fractionation assume a consistent starting composition of the heavier/lighter water molecules? If the starting composition varies over geologic time, does that need to be accounted for in the analysis?
Yes, very good question. I'm assuming that the person asking this question is referring to the ocean isotopic composition. And that's totally true. When we go back in time, especially on very long time scales, when there was more, also really big masses of water being conserved in these big ice sheets, then yes, the isotopic composition of the ocean does change also. And this is accounted for in the very long glacial interglacial interpretations. We do account for this in terms of when we interpret this, but it's actually not super substantial, but you need to take it into account to get a good temperature reconstruction, especially when you think about the DXS, because this is very sensitive to, if you only change 18O a little bit in deuterium, then the DXS will actually change quite a bit, yes.
Okay, that makes sense. Thank you so much. Okay, our next question reads, and this was submitted by Karthik Sender, and it reads, does the shifting in the magnitude and direction of seasonal winds on a yearly basis over the ice cores affect/bias sampling, with some sampling sites lying in the direction of the winds and ice being deposited more in these sites?
Okay. Yes, I think this ties in with what I said in the end a little bit, that if we think about blowing snow and wind patterns as maybe an influential factor for how the snow signal is created, then yes, it would matter dramatically, kind of, if you have in one climatic state a lot of wind, and in another climatic state you have no wind at all. And this is exactly what makes it so important that we also simulate this a little bit on longer time scales, because if we just assumed that sublimation and blowing snow and everything just stayed the same during glacials and interglacials, and it's always the same, it wouldn't matter then because we're fitting a line essentially, right? We are basically saying, okay, delta 18O versus temperature. And if this calibration function never changes, then it doesn't matter why it's created. It's just that if, for example, during the glacial, the wind was so much more important because there was actually much more wind and much more blowing snow. But now during the interglacial, it's not. Then this would actually influence this slope in time. And therefore, it's important that we get an understanding of how important it is now and how important it was back in the last glacial, for example.
I see. That makes sense. I think that definitely answered the question. But Karthik, if you need any clarifications, feel free to follow up. Okay, our next question is going to be posted in the chat. And this question reads, how do you suggest paleoclimatologists alter their interpretations or decide whether or not to alter their interpretations based on your findings?
Yeah, that's the big that's the big open question at the end of this talk, right? Well, I can only say so much that I'm doing my best to really give everybody an easy answer. Sadly, it's not always that it's really easily and with a simple answer answered some of these questions. I do think that I'm not even certain whether I'm going to say that my research points towards that we have been interpreting ice core records wrongly. I'm more saying that what if we have been interpreting them in a correct way, but for a wrong reason? So what if we would actually need to, I hope that my research actually shows that, hey, maybe there's a closer link between vapor and snow than just precipitation, which would actually make this a much better climate archive, right? If you think like in the ideal world, we would have a vapor isotope signal archive because this is there all the time. So you would have like every single event being recorded in the vapor. But of course, we only have precipitation that is conserved. So now if we have additional processes linking the vapor with the snow, then this makes the ice core a better climate archive. But I see that I'm evading the question a little bit because there's no easy answer. Yes, I think I hope that we can, with good simulations in the future, say that maybe especially glacial, interglacial interpretations need to take care to just not misinterpret some of the variations. And yeah.
Excellent. Thank you so much for that very thorough answer. Okay, our next question, also submitted by K Sender, reads, is the isotopic signal affected by organisms or microbes if they exist in the ice column? And I will add my own little question to that, or in the water, if you know, if it, I don't know whether it's precipitation or anything. Yeah, I'll leave open the interpretation to you, but
Yes.
yeah.
Okay. So really, where I'm looking at there is hardly any microbes that are using the snow as a water source. It's really striking that in the middle of Antarctica, there is not much living organisms. So we are specifically sometimes looking for them in ice cores, but really in the interior of the ice sheets where the old ice cores are drilled, there's not so much. And then I think even if, then it's certainly not that I'm aware of that this is so strong, the effect, that we are aware of it currently. I think certainly plants have a fractionating process in the way that, yes, they are using the water or can have a fractionating process. But yes, so microbes, I don't think they are just consuming the water that is there, but there's no fractionation happening in microbes, I think. Yeah.
Okay. Great. Thank you so much. It actually looks like we just got 3 questions in the chat, so perhaps we can just tackle those. So the first one was posted by Michael Hesseman and reads, "Hi, I also graduated at the University of Hohenheim. My question is all analysis based on ice cores being put into question by your findings?"
Well, I don't want to make this bigger than it is. But I mean, yes, there was always the big what if. But as I said, I think if ice core records were interpreted wrongly for the past, I don't know how many years, century, I think it would have been shown up at some point that it doesn't make sense. Like something would have broken in the interpretation, that it doesn't, it like you can see the same climatic variations in sediments and pollen and like all the other climate proxies. So I'm not fundamentally questioning ice cores at all. I'm basically just saying, hey, what if we have been using ice cores correctly, but for the wrong reason? And I think when we look into when we think about how ice cores might be used in the future, when maybe we assimilate ice core information into climate models to get like reanalysis products or stuff like this, right? There it's really essential that we have understood how these ice cores are really capturing the climate signal. So yes and no, I am questioning whether we have understood ice cores, whether we have understood the climate signal in the ice cores, but I'm not saying that the interpretations that have been done in the past years are fundamentally wrong. No, I'm not saying that.
Great. Thank you for addressing that question. Perhaps we can just move on to the next question that was posted, which reads, "Great talk. If the sublimation rates can influence oxygen and hydrogen fractionation, if so, how did you test it? Thank you."
Yes. So if I understood the question correctly, yes, the sublimation does influence the isotopic composition. Now, sorry, or do I see these as well? Yes, maybe I do. It can influence oxygen fractionation. So sublimation entails fractionation, leads to fractionation. And we tested it both by looking at the snow during sublimation and saw that there was a change happening. And we also tested it through this measuring the sublimation flux directly, measuring the isotopic composition of the sublimation flux. And this really also showed that we had fractionation happening during the sublimation. But I want to emphasize, if this is someone that is really has thought about fractionation a lot, I think my latest research also shows that I want to emphasize that we have measured snow sublimation, not ice sublimation, because it seems that there is a fundamental difference between snow sublimation, because snow is very complex. There's a lot of air in between. It's not just an ice block, right? So yeah, snow sublimation fractionates. Ice sublimation might not fractionate.
Okay, thank you. We have one more kind of question that was just posted in the chat, which reads, "Considering the influence of snow processes, could we infer from water isotope records information on the snowpack conditions?" And I can repost it, Sonja, if you can't see it easily, but
I see it now.
Okay, great.
I hope that, yeah. Yes, that's a perfect, cool question. And yes, that's what I'm actually trying and hoping to do very like currently and in collaboration with the snow community, because I do think that it's pretty fascinating that all these processes have their own isotopic signature. And hopefully we can then maybe also look at seasonal snowpack and look for, I don't know, a depth hoar layer, or how much blowing snow, how much of the snowpack is actually blowing snow being brought in versus initial snow being deposited and stuff like this. So I'm really hoping that we can use the stable water isotopes now in snow to also get a better understanding of the snow processes in general. But since this is a paleo talk community, I was concentrating on this aspect. But yes, I'm also trying to now use isotopes to understand or better understand snow processes. Yes.
Okay, thank you for that response. It looks like we're down to our last couple of questions that were submitted. So here is our next one. And this one reads follow-up. So presumably to one of the earlier questions, follow-up. Do you think the surface processes and local exchanges with vapor and snow will impact the footprint of the long-term climate signal? Do you have any modeling plans to test the effects of these local processes, to test, I guess, whether the effects of these local processes interfere with the global climate signal?
Yes. Yes, I have plans, and yes, they do. Yes, the local signal, certainly, especially with the DXS, for example. Like I said, the DXS is often assumed, I didn't go too much into detail, but it's often assumed to be a moisture source signal that is conserved and then basically can be interpreted as, let's say, a global or large-scale climate signal, because you can get information about the whole circulation, basically. And exactly, this is what I have now shown you, is that some of these local processes are also having an effect on the DXS. And then, of course, it's a little bit tricky to say, well, is it now because the moisture source changed, or is it because there's more or less wind, let's say, at the site? And yes, again, we will definitely do this with the model. That's what my Snow Dogs project is about, and I'm hoping to have some results to present to you soon. But as you've seen, I've done a lot of observational and experimental work, and now I need to transition into the modeling. And as there are presumably some early career researchers, it also takes time to learn new skills. So I'm on it.
Okay, great. Thank you so much. And now on to our last question. What were the most challenging parts of creating and using the experimental wind tunnel?
Yeah, cool question. Thanks for the question. So I was lucky enough that this wind tunnel existed already. People had been using it to test, for example, influence on snow properties. And it was both very nice to have one and like very bad because it was already there. So I couldn't design my own. Now we actually have a follow-up project, and hopefully maybe we adjust this wind tunnel a little bit. And I've shown you, I think the biggest weakness of this wind tunnel is that the turbine brings in a lot of temperature, like a lot of heat, and this really warms the airstream. And this is, of course, if you then want to directly translate your experiment results to what is happening in the real world, it makes it a little bit challenging. So this is, I think, was the biggest challenge. And yeah, so I would say temperature control of this wind tunnel was the biggest challenge, and I hope to update or like improve that a lot in the coming project. Yeah.
Yeah, well, that wind tunnel is certainly an interesting approach, and really, I think, fascinating to me at least, and I'm sure a lot of people in the audience. So thank you everyone for submitting the questions. With that, we'll kind of wrap up our seminar for today. So I just want to thank our speaker, Sonja, once again for a really interesting talk. Thanks for taking the time to be here with us today, and thanks for giving such thoughtful answers to all the questions. And thank you to everyone in the audience for attending. So just a little reminder, if you're up for it, please fill out the weekly feedback form, which will be linked in the chat here soon, so that we can learn a bit more about who attended today's seminar. We'll be meeting next week on June 17th to hear from Zekung Wang about quantitative ichnology. So that should be an interesting talk. In the meantime, you can always reach out to us at PaleoPerks via our email or our website. And we're looking forward to seeing everyone soon. So have a great rest of your day, everyone. Bye-bye.